Well, welcome to our first section in fourth quarter, and we'll be covering two chapters in this quarter. The first one will be chapter 6. We're not going to cover chapter 5. And chapter 6 is about solving trig equations. You had a small introduction to this back in Algebra 2, and we'll be extending that. We'll also be solving in radians, and some of the problems will be more complex than they were in Algebra 2. Algebra 2, again, was just an introduction to this. So our goal here is to be able to solve trig equations. And a trig equation is an equation that contains a trig function. If you look at this one, it contains sine of theta. It actually contains a sine squared of theta and a sine of theta. And you'll be solving it for values that will make it true, just as when you solved an algebraic equation. In fact, we'll be seeing that solving a trig equation is very similar to solving an algebraic equation. We'll use many of the same practices. So let's begin by looking at an algebra equation. So here we have an algebraic equation that you would have encountered back in Algebra 1 probably. And what they would have told you is to try to isolate the variable. So the variable here is x. We're going to try to get all the x's on one side. And to this end, I'm going to subtract 2x on both sides. So I have 3x plus 7 equals negative 5. Then I'll subtract 7. I have 3x equals negative 12. I'll divide by 3. I end up with x equals negative 4. And that's our solution. Now, of course, the ones that we encounter here in trigonometry are going to be a little bit more complex, but oftentimes we'll just be adding or subtracting, multiplying or dividing to isolate the trig function, not the variable itself, but the trig function. So let's take a look at a trig function that we might have seen back in our Algebra 2 course. When you're solving a trig function like this, or a trig equation, there are two things you have to consider right at the beginning of the problem. Are you working in degrees or are you working in radians? And are you restricted to just one rotation or are you able to go more than one rotation? Well, what we look for is, in our directions, we look for something like this. This tells us two things. It tells us, first of all, that we're working in degrees. And the second thing that it tells us is we're restricted to one rotation. Because obviously they've given us degrees as our limitations, and then they've also told us that we can only go from 0 to 360. Notice that the equals bar means we can include the 0, but we cannot include the 360. So now we'll try to isolate the trig function. To isolate the sine of x, I'll first add 1 to both sides, giving me 2 sine x equals 1. Did that by adding 1 to both sides. Then I'll divide by 2, and I end up with the sine of x is equal to 1/2. Okay, now at this point, once the trig function is isolated, we have to decide, is this going to be a problem that involves a reference angle, meaning comes from one of our special triangles, or is this a problem where we use the unit circle? The unit circle was used for quadrantal angles, like 0, 90, 180, 270. And of course 360 if we were allowed to use that. Well, this one involves a reference angle. There was one of the angles from our special triangles, either 30, 45, or 60, that had a sine that was equal to 1/2. And it was, of course, 30 degrees. So our reference angle here is 30 degrees. Every time you solve one of these problems, you're expected to show the step where you've isolated the trig function and show the reference angle. And now we have to decide, since we can go a full rotation, will we have more than one answer? And the answer to that question is yes. There are actually two quadrants where sine is a positive value. One of them is quadrant 1, right here. Quadrant 2 is the other. In 3 and 4, sine is negative. So we're restricted to these two quadrants. It means we'll have one answer from quadrant 1 and we'll have another answer from quadrant 2. So our quadrant 1 answer will be the same as our reference angle. The x will be equal to 30 degrees. Our quadrant 2 answer, well, in quadrant 2, we have to go 30 degrees up from the x-axis. And we're interested in this angle over here. So to get that, we'll take 180 degrees and subtract 30. We end up with x equals 150 degrees in quadrant 2. Now, that type of problem you may have solved back in Algebra 2. Some of the teachers cover that, some of them don't. But again, it's just a basic problem. We'll have some of these, but they will get more complicated. Here's our second problem. If you take a look at this second problem, well, are we working in degrees or radians? Once again, we look at this, and it tells us it is degrees. And then are we restricted to one rotation? The answer is yes, one rotation. We can only go up to 360. This time the variable is the Greek letter theta. That doesn't really change anything. We still follow the same process. We isolate the trig function. In this case, we just have to divide by 2. Then we decide, is this a quadrantal angle or is this one that's a reference angle? And this one again is a reference angle. The reference angle this time, the angle that has a cosine that's equal to 1/2, is 60 degrees. So our reference angle is 60 degrees. Now, if you recall, the notation often for the reference angle is theta hat, with a little hat on the top. Okay, and that hat's just called a caret, that symbol. And again, we have to think of the quadrants. So the cosine is positive. Cosine is positive in quadrant 1, because all of the trig functions are positive in quadrant 1. So that would be theta equals 60 degrees. Reference angles are quadrant 1 angles. And the other quadrant where cosine is positive is quadrant 4. So in quadrant 4, we have to go 60 degrees down from the x-axis. And then to figure out what this angle is, we would take a full circle, 360, and subtract 60. So we find out that in quadrant 4, we have 300 degrees. Now, of course, the problems are going to get continually more difficult. So let's take a look at another. When you look at this one, we have to decide, are we in degrees or radians? This one, once again, is degrees. Is it one rotation or can we go more than one rotation? And the answer here is we're restricted to one rotation. We'll isolate the sign. We do that by subtracting a square root of 3 and dividing by 2. So the sine of theta would be equal to negative square root of 3 over 2. And this step must be shown every single time where you've isolated the trig function. That's worth points on anything that's graded. Then you have to decide, is it a reference angle or is it quadrantal? This one again is a reference angle. So we don't consider the negative. We're looking for an angle in degrees where the sine is square root of 3 over 2. That one is 60 degrees. Oh, sorry, that one is 60 degrees. Which quadrants are we in? Well, sine is negative. Depending upon how you remember this, we have the little saying, all students take classes. So if sine's negative, that would be in these two. So we're looking at quadrant 3 and quadrant 4. In quadrant 3, that means we've gone 60 degrees beyond the x-axis. So we would have to take 180 and add 60. So in that quadrant, theta would be equal to 240. In quadrant 4, we've seen that already. In quadrant 4, we're 60 degrees this time short of 360. So we're taking 360 minus 60. So in quadrant 4, we once again have 300 degrees. Let's take a look at a third example. Now, this third example is a little bit more complicated because in this third example, we do have the trig function on both sides of the equation. And we're in radians this time. So we've noticed by this part of the directions, we are in radians, but we are still restricted to one rotation. We stop at 2 pi. Well, the first step is to try to get all of the trig functions on one side. And I'm going to subtract 3 sine t first. That will give me square root of 3 plus 2 sine t equals 0. And then I'll subtract square root of 3. And I'll divide by 2. Hey, this looks very familiar. In fact, we just finished one where the sine was equal to a square root of 3 over 2. So our reference angle, we remember, was 60 degrees, but in radians, that would be pi over 3. We remember that the quadrants we use for negative signs are quadrants 3 and quadrant 4. But again, we're in radians. So in radians, if I'm going a pi over 3 beyond, well, this is a full pi being 3 pi over 3. So I would have 3 pi over 3 plus 1 pi over 3, and I get 4 pi over 3. In quadrant 4, well, I'm a little short of a full rotation. In fact, I'm pi over 3 short. All the way around would be 6 pi over 3 because it's 2 full pi's. So I have to take 6 pi over 3 and subtract pi over 3, and I get 5 pi over 3. Okay. If you need to pause on this one and look at it again, feel free to do that. Here's another one. Degrees or radians? Well, you can see if you look at this that we're in radians again. Still restricted to one rotation. By the way, you may think, are we ever not going to be restricted to one rotation? Yeah, most definitely we'll have some where we're not restricted to one rotation. So this time I have to subtract a 4. And that gives me 0. And then I have to divide by 3, and I get sine of t equals 0. Well, this one is not a reference angle. This one is quadrantal. So if you think back to our unit circle looked like this. Each of these points on the coordinate axes had an ordered pair associated with them. This one was over 1 and up 0. This one was over 0 and up 1. This one was left 1 and up 0. This one was over 0 and down 1. And the radius, of course, was 1. And here we use the circular definitions. Recall that the sine of an angle was defined to be the y over the r. So in this case, we need the y to be 0. Well, the y is 0 at this point and at this point. So there are 2 places where y over r is going to give us 0. Well, this one corresponds to 0. So that would be t equals 0. Again, these are quadrantal. This one over here corresponds to pi. So we have t equals pi. Again, if you need to pause on this one, feel free to pause and look at it closer. And go through the explanation again if you need to. Number 5. Now, if you look at this one of the things that it tells us is we're going to need to use a calculator. It also tells us that we're going to be rounding to the nearest tenth of a degree. So you'll need your graphing calculators on this one, or you can use the calculator or any scientific calculator that has the trig functions on it. We still follow the same process. We're still going to try to isolate the trig function. So I'll subtract 3 cosine theta. That'll leave me with a single cosine theta minus 1 equals 4. And then I'll add 1 to both sides. Cosine theta equals 5. Now this one definitely is not one of our reference angles. None of our reference angles, 30, 45, or 60, had a cosine equal to 5. It's also not quadrantal. None of those. So if we were looking for a reference angle, we would have to take the inverse cosine of 5. But if you do that, your calculator will come up with an error. And that's because if you remember the graph of the cosine never went above 1 nor below -1. So there is no angle theta. So for this one, we would have to say no solution, because nothing will work on that one. Okay, let's take a look at number 6. Now, number 6 is an algebra problem. We would have solved this one probably using factoring. So I'll subtract 5, because we need it set equal to 0. I can't factor out any common factor, so instead, I'll try to factor it as a general trinomial. The front ones have to multiply to give me 2x squared. Not many choices there, 2x and x. The back ones have to multiply to give me 5. Not many choices there either, 5 and 1. I think I'll need to put the 5 here and the 1 here. And then if I want a -9 in the middle, I'd put a negative there and a positive here. On the outside I get -10, on the inside I get +1, and that gives me the -9x. Then I set each of those factors that contains a variable equal to 0. Here I end up subtracting 1 and dividing by 2. Here I just add 5. Now, of course, this isn't the problem we're going to have in our trig class. We're going to have a trig problem where we factor. So let's take a look at one of those. First of all, are we in degrees or radians? Well, according to this piece right here, we're in radians. We're still restricted to 1 rotation. But you'll notice the coefficients are the same coefficients we just had. The 2, the -9, and then the 5 on the other side. So we're going to follow the exact same process. I'm going to subtract the 5 first. And then I'm going to factor just exactly the same way I did before. Now, what's different here is, instead of an x, we have a cosine. So 2 cosine squared t, I'm going to need to factor that into 2 cosine t and a single cosine t. The 5 and the 1 will go in the same place. This will still be minus, and this will still be plus. We'll still set each of those factors equal to 0. 2 cosine t plus 1 equals 0, and cosine t minus 5 equals 0. On this one, the first one rather, we'll still subtract 1 and divide by 2, giving us cosine t equals -1/2. Now we'll come back to that one in a moment, but on the other one, to isolate the trig function, we'll just add 5. Cosine t equals 5. Again, this step where you have them isolated has to be shown every time. If there's factoring involved, the factoring step has to be shown as well. So when we're talking about this first one right here, it's going to be a reference angle problem. So we're in radians. We're looking for the angle whose cosine is +1/2. Let's see. In degrees, it would have been 60 degrees. So in radians, it's going to be pi/3. It's a negative cosine. Cosine's negative in quadrants 2 and 3. In quadrant 2, I would have to take a full period, or a full pi rather. A full pi would be 3 pi/3, and I'll have to subtract a 1 pi/3. So I get 2 pi/3. In quadrant 3, I have to take a full pi, which is 3 pi/3, and I have to go beyond it by a pi/3. So in quadrant 3, I get 4 pi/3. Now for this other one right here, we've seen that before. Remember, the sine and cosine functions were bounded. They never went higher than 1 nor lower than -1. So for this piece of it, we'll have to say no solution. But we won't box no solution. The reason we don't box no solution is, as you can see, we already found 2 solutions. The only time you would box no solution as an answer would be if there was no solutions at all to the entire problem. Okay. This last one, it says, we're going to use the quadratic formula. The quadratic formula was the formula that some of you memorized with a little song. It's a negative b plus or minus square root b squared minus 4ac all over 2a. And we use it when we can't factor. So this one does not factor for us. It doesn't factor. The unknown is cosine theta, so I'm going to have cosine of theta equals, now negative b will be the negative of, oops, sorry about that. Will be the negative of -4, because b is -4, and then plus or minus the square root, and then b squared would be -4 squared minus 4 times the a times the c, and all of that, every bit of it all the way to the front, is divided by 2 times the a. So that's just your regular quadratic formula. But take note that it isn't theta that's equal to that, it's the cosine of theta that's equal to that. So now, we're going to have to work that out. Now, the negative of -4 is just going to be +4, plus or minus the square root, and now we can use our calculator. So I'd have 16, that's -4 squared, plus 8, 16 minus 8 rather. So I just have a square root of 8 all over 4. Now there are really 2 possibilities here. One of them is the cosine of theta is equal to 4 plus the square root of 8 over 4. But if I take 4 plus the square root of 8, and I get that total, and then I divide that by 4, I get 1.7071. So cosine of theta equals 1.7071, and it keeps going. We just said cosine can't be bigger than 1. So that part of it is going to give us no solution. Let's see about the other part. The other part would be the cosine of theta equals 4 minus the square root of 8 over 4. Well, if I take 4 minus the square root of 8, and I get that total first, and then I divide that by 4, I end up with cosine of theta equals 0.292893, and it keeps going. That one's going to give us some solutions. But that one is not one that's one of our reference angles from our special triangles. It's also not quadrantal. So in order for us to get our answers, we have to get the reference angle by taking the inverse cosine of that 0.2928932188. And our reference angle then comes out to be 72.96875154. Now, sometimes the reference angle is one of our answers. Sometimes it's not one of our answers. So we came out with a positive cosine. positive cosine means we use quadrants 1 and 4. So we actually are going to use that reference angle. It told us to round it to the nearest tenth. If I round this to the nearest tenth, it looks like theta would be equal to 73.0 degrees. In quadrant 4, well, I'd have to take 360 minus the reference angle. And if I take 360 minus the 72.96875154, and I round that to the nearest tenth, I get 287.0 degrees. Again, if you need to look at that one more time or go through it again, please feel free to do that one. This is your assignment, and I'm not going to be collecting the homework. The entire worked out key is up on Schoology. You're welcome to look at it. And I will have office hours, so feel free to log in using the link to the Teams app during the office hours and ask questions if you need them. Good luck on it. I hope this first lesson goes well for you.